Hello everyone. Previous lecture we have studied the concept related with the chapter conics, and in that we define the parabola. We consider the standard equation of the parabola, that is standard forms of the parabola, and we see some important examples related with the parabola. Now in today's lecture we go with our next part, and in that we define the ellipse. Here to define the ellipse, we consider here our first figure. Here L, this L is our axis, then M is the generator. We consider M. Here L and M are the two lines. Here two lines. Okay. Here L is called the axis. M is called the generator. Okay. Here we rotate this M about this L. I repeat again. Here we rotate this M along this axis, that is along this L. Then we get this type of cone, this type of figure. Okay, and here we have to consider the intersection in between these cones and the axis and this and the plane. Okay, so here we consider this plane. This is our plane. Okay, here we consider the intersection in between this plane and the cone. Okay, here we consider the plane, or we intersect this cone obliquely by using our plane, and this plane does not pass from the vertex V and does not parallel to the generator. Okay, I repeat, this plane is not parallel to generator and not passing through the vertex. Then we get this type of figure in the intersection. Okay, and this is for the ellipse. This is for the ellipse. Okay, so here in this figure we consider the coordinate axis. Here is our x-axis, here is our y-axis. Here we define the standard equation of the ellipse, that is standard form of the ellipse. Here to define, we consider one fixed point. This is our fixed point and we call this as x. Then we consider one fixed line. This is our fixed line. Okay, and this point fixed line is our D, and this fixed line is called the directrix. We call this as directrix, and this fixed point S is called the focus. It's called the focus. If we join this fixed point and the fixed line by using this point, we consider one point, and remember here for the ellipse we consider set of all the points. Set of all the points, or the collection of the points which are equidistant from the fixed point and the directrix. Okay, so here we join this fixed point and P like this. Then we join this point P and the fixed line. Here the fixed line or point on this fixed line is M. So here we consider the ratio in between the SP and the PM. Here this SP, that is length of SP and length of PM, here always constant. Here is always constant. And here this constant ratio is called eccentricity, and we denote this eccentricity by using small e. Then here I write this as SP is equal to EPM, and this is called the focus directrix property. This is called the focus directrix property. And to define the ellipse, this E is very important. That is, the nature of E is very important. If this E lies in between 0 and 1, here I repeat, here if this E lies in between 0 and 1, that is here 0 is less than E is less than 1, then here we define the ellipse. Here we define the ellipse. So this ratio or this property is very important and is called the focus directrix property. Okay, here equation to define the equation of the ellipse. Here we consider another figure. Here we consider one figure. Okay, here again this S is the fixed point. This line we call this as D is called the fixed line. Okay, and we call this as directrix. Here we join SP and PM. Here SP upon PM is always constant and we call this as E, that is eccentricity, and we get SP is equal to EPM, and here 0 is less than E and less than 1. Okay, then here we consider the L and L dash. Here remember A. Here A and A dash are on x-axis, then B and B dash are on y-axis. Here this x-axis is called the major axis and this y-axis here is called the minor axis. This y-axis is minor axis. That is A and A dash are on major axis and B and B dash are on minor axis. Okay, so here these are the points on the ellipse. A dash, B dash are points on the ellipse. If here or here this OA distance, that is coordinate of A, we consider this as A0, and here for A dash coordinates are minus A0. Then here for B our coordinates are 0B, and for B dash we consider 0 minus B. Then we consider one line, one chord here, L dash. Here L dash is a perpendicular to the major axis, that is perpendicular to the here x-axis, and this L dash is a passing through S, that is passing through the focus. Since this chord L dash passing through the focus and perpendicular to the major axis, here is called latus rectum. Here L dash is for latus rectum, and here coordinates of this latus rectum are here L equivalent to AE B square upon A. This is for A. Then L dash minus AE B square upon A. Firstly, here remember coordinates of S are here AE 0, and for S dash we consider here minus AE 0. So these are the coordinates of S and S dash. That is the coordinates of the focus, coordinates of the fixed point. Then remember these coordinates of the endpoints of latus rectum. Here are L is equivalent to AE B square upon A, and L dash is having minus AE B square upon A. Here length of these two focus. Here S and S dash are for focus, that is length of the foci here is 2A. Here is 2A. Then length of here latus rectum. Length of the latus rectum here is 2B square upon A. So this is all about the ellipse. Here we define the major axis and minor axis. We define the points on the ellipse. Here we define the latus rectum, length of the latus rectum. Then also here the length of A and A dash. Since coordinates of A are A0 and for A dash it is minus A0, your length of A dash here is 2A. Here is 2A, and for your B and B dash it is 2B. Length of B dash here is 2B. Also here the length in between length in between the directrix, that is distance in between the directrix here is always 2b upon a, that is z dash. Length in between z dash here is always 2a upon e. So this is all about for the ellipse, and for this type of ellipse here is our equation, or equation of ellipse is x square upon a square plus y square upon b square is equal to 1. So this is called standard equation of the ellipse. This is standard equation of the ellipse. Now here condition is very important. Here whether this a is greater than b or b is greater than a. Here for this figure a is greater than b, that is length of OA. This length of OA is greater than length of OP. Then we get this type of figure. If this b is greater than a, if this b is greater than a, then the figure, this AA dash or this more length is on the y-axis, is on the y-axis. Okay, so here we consider one table to define some formulas. Okay, here for standard equation of ellipse, if BA is greater than B, then x square upon a square plus y square upon b square is equal to 1. And if here b is greater than a, our equation is again x square upon a square plus y square upon b square is equal to 1. Then center, here for the center we consider the origin, and coordinates of origin are here 0, 0. Next, here axis of symmetry, here axis of symmetry is along x and y axis. Here is our x-axis, here is our y-axis. So here to define the ellipse, we consider x and y-axis and axis of symmetry on this coordinate axis. Okay. Then vertices. Here we define here a dash, b dash are the vertices of the ellipse, and here coordinates of a are a0. For a dash it is minus a0. For b here 0b, and for b dash here 0 minus b. This is for first equation. Then for the second also here vertices are same. Then length of major axis. Length of major axis. Here length for major axis we consider as 2a, that is distance in between a and a dash here is 2a. Then length of minor axis. Here minor axis, that is point on the minor axis are b and b dash. So distance in between b and b dash here is 2b. Okay. Then for foci, here to define the foci we consider distance in between we consider s and s dash. These two are the foci. Here coordinates of s are a, e, 0, and coordinates of s dash, here s dash is minus ae 0. Then distance between the foci, that is distance in between s and s dash. Distance in between s and s dash here is twice ae. Remember this part, this distance. Okay. Then equation of directrix. Here equation for this directrix D. This directrix D here is x is equal to a upon e, that is here x minus a upon e is equal to 0. Then for the next directrix, since we have two foci, here we define two directrix. Here for this D dash equation is x is equal to minus a upon e, that is x plus a upon e is equal to 0. So for the D equation is x minus a by e up is equal to 0, and for D dash here we have x plus a upon e is equal to 0. And distance between these two directrix, distance in between z and z dash here is twice a upon e. Here is twice A upon B. Similarly, we define for the ellipse, here x square upon a square plus y square upon b square is equal to 1, and here we consider condition b is greater than a. Okay, if b is greater than a, here the length of the major axis is 2b, length of minor axis here is 2a. Okay, then for foci, here coordinates are here s 0 BE, and for S dash coordinates are 0 minus BE. Then distance between the foci, that is distance in between S and S dash. Here S and S dash is here 2 BE, and here equation of directrix. If we have this type of equation, here directrix is like this. Here directrix is like this. For this line, equation is here y is equal to b upon e for this d1, and for d dash we have x is equal to minus b upon e, and the distance between these two directrix here is twice a upon e, So in this lecture we define the ellipse, we define the standard equation of the ellipse, and we define this table. So this table is very important to solve the examples of the ellipse. So this is all about our today's lecture. In next lecture, we see some important example related with this table and related with the ellipse and related with this table. Thank you.